This video lecture covers density. Support for the development of this lesson has been provided by the National Science Foundation through the Ohio University Boat of Knowledge in the Science Classroom program. Let's start this lesson with a quick experiment. We have a marble, an air-filled ball, a water balloon, an air-filled balloon, and an apple. If we place these objects in water, which do you think will float and which will sink? Think about this question for a minute and discuss what you think will happen with the person sitting next to you. Did you guess correctly? If not, which ones were different from your original guess? We see the air-filled balloon and air-filled ball float, the water-filled balloon and apple seem to hover, and the marble sinks. Why do some of the objects float while others sink? The answer is density. Let's find out what density is and why it's so important in determining whether an object will sink or float. First of all, what is density? It's an intensive property, which means it's always the same for a given material, no matter how much of that material you have. For example, one brick and a ton of bricks have the same density. Density is a measure of compactness. It tells us how much matter is in a given volume. That means that if I have two objects with the same volume but different densities, the object with the higher density has more matter packed into that volume. Now that we have an idea of what density means, how do we give it a value? If density describes the amount of matter per a given volume, we can write it as the mass divided by the volume. In equation form, we write D equals m over v. This equation is easy to remember. The m over v is like a heart, so all you have to know is I love density. So why is density important? What do we use it for? We know from our demonstration that it dictates whether an object will float or sink. But think about some actual applications where knowing this is important. Did you know that density is used to design ships, submarines, and airplanes? Density can also be used to identify materials since it's an intensive property. Did you know that density is also responsible for convection currents in the ocean, atmosphere, and the Earth's mantle? Let's go back to our float or sink question. Why do some objects float while others sink? We answered density, but what is it about density that makes an object float or sink? If we have an object that's density is greater than the density of the fluid, the object will sink. But if the object has a density that's less than the density of the fluid, then the object will float. So how can a steel ship float while a small steel ball would sink in water? Let's think about the difference between the ship and the ball. The ship is shaped in such a way that most of its volume is filled with air. This means there's not as much mass packed into the volume, so it's less dense than the steel ball, which has a lot of mass packed into its volume. Then how do submarines work? How can they stay afloat sometimes and be submerged other times? Submarines have ballast tanks that are used to help it surface and submerge. When the submarine is at the surface, its ballast tanks are filled with air. To submerge, the air is released and the ballast tanks fill with water. When it's time to surface again, the water is released and the ballast tanks are filled with air again. So far, we've talked about the first two reasons why density is important. But now let's talk about how density can be used to identify materials. This can be a simple or complex problem, depending on the situation. If we have an object that's only made up of one material, and it has a volume that's easy to determine, like a cube or a sphere, then the problem is very simple. But if we have a mixture of materials, or a shape that we can't calculate a volume for, then the problem becomes more difficult. Let's start with an easy problem. You're given a cube of wood with a mass of 96 grams and dimensions of 5 centimeters. Use the table below to determine what kind of wood this cube is made of. What should we do first to solve this problem? Let's start by identifying what we're given and what we need to find. We were told that the mass of the cube is 96 grams, and its length, width, and height are 5 centimeters. We're trying to find out what kind of wood this cube is made from, so we need to find the density. Now we can start solving the problem. Since we know we love density, we can write density as mass per volume, or D equals m over v. We were given the mass of the cube, but we need to calculate the volume. We know the volume of a cube is length times width times height, so we get 125 cubic centimeters for the volume. Now we can plug these values into our density equation and solve. Remember to always put your units. This will help you make sure you're using the correct numbers and you have the right units. We'll write D equals m over v, which we know is 96 grams over 125 cubic centimeters, which gives us a density of 0.77 grams per cubic centimeter. If we go back to the table we were given, this is the density of American white oak. Now let's talk about a harder problem, the problem that was given to Archimedes by the king of Syracuse. As the story goes, the king gave a jeweler some gold and told him to make a crown out of it. When the jeweler finished, the king was suspicious that the jeweler stole some of the gold and used a mixture of metals for the crown. But the king didn't know how to prove that the crown wasn't pure gold, so he went to Archimedes and asked him to find out if the crown was pure gold. Archimedes finally came up with the solution in an unlikely place, the bathtub. He realized that when he sat in the bath, the water level rose and spilled out over the edge of the tub. He also noticed that the amount of water that spilled out depended on how much of his body was submerged in the water. This would give him a way to find the volume of the crown. According to legend, Archimedes was so excited to have found the solution that he left his clothes at the bathhouse and ran home shouting, "Eureka, Eureka!" He started with a piece of gold and a piece of silver with equal weights, and noticed that the silver displaced more water. It had a larger volume because silver is less dense than gold. He did the same with the crown and a piece of gold with the same weight. If they have the same weight and are the same material, they should have the same volume and displace the same amount of water. But the crown displaced more water, meaning the jeweler had cheated the king. This idea was called Archimedes' Principle, and it has two parts. First, that the volume of displaced water equals the volume of the submerged portion of the object. We can write this as an equation, V of water displaced equals V submerged. Second, that the force that supports an object immersed in fluid equals the weight of the water displaced by the object. This force is called the buoyant force, and we can write this equation as F sub B equals weight of water displaced. How are the two parts of Archimedes' principle related? We can find the buoyant force if we know the volume of water that is displaced. If we start with our equation that F sub B equals weight of water displaced, and remember that weight is mass times acceleration due to gravity, we can write that F sub B equals m of water displaced times g. How can we relate this to the volume of water displaced? Remember that mass and volume are related by density, D equals m over v. We can rearrange this equation to get mass by itself, and we have D times v equals m. This means we can substitute D times V for m in the buoyant force equation, and we get the buoyant force is equal to the density of water times the volume of water displaced times the acceleration due to gravity. This relationship between the two parts of Archimedes' principle helps us to solve problems. Buoyant force can either be less than, greater than, or equal to the weight of the object. If the weight of the object is greater than the buoyant force, the object will sink, and this is called negative buoyancy. If the weight of the object is equal to the buoyant force, the object will hover, and it's called neutral buoyancy. Finally, if the weight of the object is less than the buoyant force, the object will achieve positive buoyancy and float. Buoyant force is also responsible for another phenomenon called apparent weight. Apparent weight is the weight of an object when it's submerged or partially submerged in water. If we look at the picture below, we see that the apparent weight is less than the actual weight. Why do you think this is always true? Let's look at the forces. When the object is in the air, the only force acting on it is its own weight pulling down. This force is what gets measured by the scale as the object's weight. When we put the object in water, it still has its full weight acting down, but it also has the buoyant force acting up on it. The difference between the weight and the buoyant force is what the scale measures as apparent weight. Therefore, apparent weight must always be less than the actual weight. Let's use Archimedes' principle and try another problem. You want to identify a 195-gram rock you just found. If you find the volume of the rock using the graduated cylinder shown, what kind of rock did you find? Let's start by identifying what we've been given and what we need to find. We know the mass of the rock is 195 grams. When we put the rock in the graduated cylinder, we notice the water level rose. What does this tell us? It tells us the volume of water displaced by the rock, which is the final volume, 260 cubic centimeters, minus the initial volume, 200 cubic centimeters. That gives us the volume of water displaced is 60 cubic centimeters. We want to know what kind of rock we found, and we'll use density to do this, so we need to find the density. How can we use the information we were given to find the density of the rock? First, let's remember that density equals mass divided by volume. We were given the mass of the rock, but how do we know the volume of the rock? We can't apply a simple volume formula like we did for the cube of wood, but we can apply Archimedes' principle. We remember that Archimedes told us that the volume of water displaced by an object is equal to the volume of the object that's submerged. Since the entire rock is submerged in this case, we know that the volume of water displaced must equal the volume of the rock. That means the volume of the rock is 60 cubic centimeters. Now that we know both mass and volume of the rock, the rest of the problem is very easy. We just plug the numbers into our formula and calculate the density. The density is 195 grams divided by 60 cubic centimeters, which gives us 3.25 grams per cubic centimeter. If we look at the table we were given with the densities of the different rocks, we see that the density of our rock falls within the range for peridotite. Let's try another problem with Archimedes' principle. This time we're going to use the idea of buoyant force. A standard basketball with a mass of 624 grams and a diameter of 24.3 centimeters is held fully underwater. Calculate the weight of the ball and the buoyant force. When the ball is released, does it float or sink? Let's do like we did before and write what we're given and what we need to find. We're told the mass of the ball is 624 grams and the diameter is 24.3 centimeters. We are asked to find three things: the weight of the ball, the buoyant force acting on the ball, and whether the ball will sink or float when it's released. Let's start by finding the weight of the ball. We remember that weight is mass times acceleration due to gravity. We know the mass of the ball, and we know acceleration due to gravity is 9.81 meters per second squared, so we can put in the numbers and solve. But in order for the units to be compatible, we need to convert grams to kilograms. We can do a quick dimensional analysis while we write out the equation. We know that there are 1,000 grams in a kilogram, and we want to change from grams to kilograms, so we should divide by 1,000 grams so that the grams cancel out. If we complete our calculation now, we find that the weight of the ball is 6.12 kilogram meters per second squared. Remember that a kilogram meter per second squared is also called a newton, so we can write the weight of the ball is 6.12 newtons. Now let's move on to the second part of the problem, finding the buoyant force. We know from Archimedes' principle that buoyant force equals weight of water displaced. But how can we find the weight of water displaced? Let's start by making some substitutions. Since we know that weight is mass times acceleration due to gravity, we can write buoyant force equals mass of water displaced times acceleration due to gravity. We know acceleration due to gravity is 9.81 meters per second squared, but how do we find the mass of water displaced? What relationship do we have for mass that will get us to values that we already know? Remember that we can substitute density times volume for mass. So we can write buoyant force as density of water times volume of water displaced times acceleration due to gravity. Now, we know the density of water and acceleration due to gravity, but how can we find the volume of water displaced? Let's consider what we were given in the problem statement. The mass of the ball and the diameter of the ball. We already know why we were given the mass of the ball, to calculate the weight. But what might we use the diameter for? We can use the diameter to calculate the volume of the ball, and we know from Archimedes' Principle that the volume of water displaced equals the volume of the object that's submerged. So we can replace volume of water displaced with volume of object submerged. We end up with buoyant force equals density of water times volume of the object submerged times acceleration due to gravity, all of which we know. Let's start substituting in our values and do the calculation. Density of water is 1,000 kilograms per cubic meter. Again, remember units. We want to end up with newtons, so we should work with kilograms and meters. Since the ball is a sphere, the volume can be calculated from 4/3 times pi times the radius cubed. Notice that we need to be careful of two things when we calculate the volume of the ball. We were given diameter, not radius, and it was given in centimeters, not meters. That means we need to divide the diameter by 2 to get the radius and convert from centimeters to meters. We can do a dimensional analysis again, knowing that there are 100 centimeters in a meter, and we want centimeters to cancel. So we put the 100 centimeters on the bottom and meters on the top. If we calculate this out, we find that the buoyant force acting on the ball is 73.7 kilogram meters per second squared, or 73.7 newtons. Now we can answer the last part of the question. Will the ball float or sink when you remove your hand? Remember from before that the object will float, sink, or hover based on how the object's weight compares to the buoyant force. Our basketball has a weight that's much smaller than the buoyant force, so the buoyant force will push it up and it will float. This is an example of positive buoyancy. We can also answer this question visually by looking at the forces that are acting on the ball after we release it. We only have the weight of the ball acting down and the buoyant force acting up. Since the buoyant force is much greater than the weight of the ball, the resultant force will be acting upwards, pushing the ball to the surface of the water. When we started this lesson, we listed 4 reasons why density is important. Do you remember those reasons? We said it dictates whether an object will float or sink, that it's an important factor in the design of ships, submarines, and airplanes, that it can be used to identify materials, and that it's responsible for convection currents in the oceans, atmosphere, and Earth's mantle. So far, we've discussed the first 3. So let's talk about the 4th point, convection currents. Convection currents occur when a warm fluid and cool fluid interact. The molecules in the warm fluid are excited and moving apart, while the molecules in the cool fluid are closer together. It's easy to remember which is which if you think about yourself when you're warm or cool. If you're hot, you don't want a lot of other people around you, so you spread out. But when you're cold, you huddle close together. It's the same idea with the molecules in a warm and cool fluid. Now, what does all this have to do with density? If we look at the diagrams for the warm fluid and the cool fluid, we notice that for the cool fluid, the molecules are packed in close together, so more molecules fit into the space. Remember how we describe how much matter is packed into a given volume, with density. Since the warm fluid has fewer molecules per unit volume than the cool fluid, the warm fluid is less dense. So what does this tell us about how convection currents work? Well, since we have a warm fluid with low density and a cool fluid with high density, that means the warm, less dense fluid will rise to the surface, while the cool, more dense fluid will sink. Density is the reason why hot air rises and cold air sinks. When the hot air rises, it cools, becomes more dense, and sinks back down, where it warms as it passes over land and rises again. The same is true of convection currents in the ocean and the Earth's mantle. There are 2 labs that go with this lesson, the floater sink soda pop experiment and the penny density experiment. Through the floater sink soda pop experiment, you will investigate how the addition of solvents, such as sugar or salt, can affect a liquid's density. You will first develop an initial hypothesis stating whether the addition of solvents increases or decreases the density. You will then test your hypothesis using different soda pop types, including different brands, regular, diet, and zero-calorie sodas. To complete the lab, you will record the name of the soda pop, place the pop in the water and note whether it floats or sinks, then remove the can and pat it dry. Measure and record the mass of each can. Calculate the density, assuming the volume is 13 fluid ounces or 384 milliliters, and record the mass of sugar for each can. You will then complete the calculations and questions attached to the lab procedure handout. During the penny density lab, you will apply your knowledge of Archimedes' Principle to study how the composition of the penny has changed throughout its years of existence. The composition of the penny has changed several times since its introduction into circulation in 1793. The most recent changes occurred in 1962 and 1982. To determine how the penny composition has changed, you will perform the following steps. First, measure the mass of 5 pre-1982 pennies. Add 5 more pennies and measure the mass. Repeat until you have measured the mass for 25 pennies. Measure the volume of the pennies by water displacement. As with the mass, begin with 5 pennies and record the water displacement. Repeat until the water displacement has been recorded for 25 pennies. Avoid splashing the water, and do not remove the pennies until all 25 have been measured. Repeat steps 1 through 3 for the post-1982 pennies. Once you've completed all the steps, you will complete the calculations and answer the questions attached to the lab procedure handout. There are also 2 additional activities you can do with this lesson: layering liquids and colorful convection currents. This activity will demonstrate how liquids will separate into layers based on their density. The key to getting to layers is to first decide what order the liquids should be added into the graduated cylinder. Use the densities given to decide the layer order, then start adding 10 milliliters of each liquid very carefully. Note that the liquid you rank as 5 will be the last layer you add, since it should be at the top. Try to avoid getting any of the liquids on the sides of the graduated cylinder, and pour each liquid slowly in the middle of the graduated cylinder, making an effort to keep the new liquid from shooting down through the other layers. Through this activity, you will explore the role that density plays in forming convection currents. You will use colored hot and cold water to observe the convection currents. You can perform this lab by following these 4 steps. First, fill 2 of the bottles with cold water and the other 2 with hot water. Add yellow food coloring to the hot water and blue food coloring to the cold water. Place an index card over the mouth of the hot water bottle, and carefully invert the bottle and place it directly over the cold water bottle. Remove the index card and observe what happens. Finally, repeat step 3 with the second set of hot and cold water bottles, this time placing the cold water bottle on top, and observe what happens. There are also 2 expansion activities that you can complete: a boat design competition and a calculation worksheet. For the boat design competition, you will assume the role of an engineer. Your engineering firm has been asked by a prominent supplier to build a boat that will be able to carry their cargo. You must build the boat using the materials you have on hand at your office. You can use no more than 56 grams of polymer modeling clay, and you will test how many pennies it can hold before sinking. You must complete the attached calculations and submit your proposed boat design to the supplier. Of course, you will be competing with several other engineering firms, and the best design will be awarded the contract. The best design will be selected according to a ratio of cargo mass to boat mass. Additional calculations are included on a worksheet to help you practice the concepts that have been covered in this lesson.